So this is the labs. Once we get through with our logic lab, we went over every one of those, right? Oops. I'll go ahead and turn your lab book into LD4. I know what that means. That's in the LD section, lab 4, right? So this should be the circuit, figure 22, right? Everybody there? This is the circuit we're going to have to connect. Of course, it's showing it in two different configurations. What type of drawing is this at the top? Starts with a W. Now that's a wiring diagram. Real hard to figure out, ain't it? The circuit's there. I mean, if we trace it through, here comes to a fuse and it comes to a stop button. There's a stop button. On the other side of the stop button, I come over here, I jump to the start button, then I jump over here and go over to the what? Go to a contact, which would be this contact right there. We're using the normally open contact. Then we come back over here and it goes back over to the where? Start button. So that'd be that guy right there. And then if we look right here, we got a jumper that goes right here. This goes over to the light, which would be this guy right here. And then it also jumps down to the coil. Here's the coil right here. So wiring diagrams are okay, but it's really hard for us to wire the circuit by, right? You understand that? So what they included here, of course, is they've included the ladder diagram. So this and this are exactly the same. But now, so the ladder diagram shows how everything is logically placed, right? You understand that? Now we do have a little problem in that they gave y'all some pin numbers, which has nothing to do with the pin numbers that we have on our control relay. So here's our control relay. And of course, it's a little tiny thing, right? You can actually see the 3 poles. It's a 3-pole double, it's a 3-pole, which means there's 3 sets of switches in here, and then each one of them can be placed in 2 directions, right? So this is 3 poles, because there's 3 switches in there, or 3 contacts in there, that can be placed either in two different positions. So 3-pole double throw would be what this relay is labeled. This is the coil. So the coil is between which 13 and 14, right? Are you okay? Okay. Now what does it say on our lab? I don't know what it says for the coil, but this is what we have. So this is a situation where you're going to ignore the numbers in your lab book and you're going to wire it according to our control relay, right? Now, of course, what we need is what do we need? Oops, I can't do that in full. So we need, I don't remember writing on it. So we need 1 contact. What type of contact is it? What's that? It's only open, right? Everybody okay? This is our coil or control relay. This is a 3-wire diagram, right? Or a sealing circuit or a memory circuit. So we have several choices on which normally open we're going to use. Of course, I've gave you all the numbers here. We have a normally open between 9 and 5. right? You understand that? We have a normally open between 10 and 6, and we have a normally open between 12 and 8. And that's why we got all these different, a lot of connections to this relay, right? This is the manufacturer's numbers, right? So when I transpose these over to my diagram, I already have this done for you. I've got 9 and 5, so it'd be number out, and then on your relay I have what? 13, 14. I didn't label the light for you, and I didn't label the push button. So how's the circuit going to work? So what's required to cause it to do anything? That is, press the start button. As soon as you press the start button, what's going to happen? It's going to energize the relay, right? Which is all, but it's also going to do what? Turn on the light, right? At the same time. Then I release the start button. What's going to happen? Well, as soon as the relay energizes, it's going to clear this, going to close that guy, and now it's got a secondary path. So this guy's going to seal in, right? You understand? Now, one of the things they're going to have you do is they're going to play around with it, and then they're going to have you energize it, and then they're going to have you kill the power. What's going to happen when you kill the power? The relay and the light's going to, the relay's going to drop out, and the light's going to turn off. And then we'll put the power back on. What's going to be required for you to energize that thing again? And this is a very popular circuit in industry. So that way, if you have a power failure and the power comes back on, all these motors are not just going to come up and do what? They're not going to run until you go over there and decide when they run again, right? You understand? This circuit's a real good circuit. Not only does it allow us to use push buttons instead of switches. If the power fails, we have to go back and re-energize the circuit. We determine when we energize the circuit. So having things just come back on when people's out there not expecting it is not good, right? So that's what y'all gonna have to do. Are you okay on this circuit? Y'all got any questions on this guy? Yes or no? Because when you do the lab, we're in the 4th week of the term, so we're gonna start getting more strict on this. So if you got questions, you need to answer them now.
Up above, like on the top circuit where it says 5, above that, there's not a number, but it's crossed out. Do we have to have a number for that?
No, y'all not gonna deal with, you're not gonna deal with this at all. So what you're gonna do is you're gonna just ignore this guy. Because this would be, we're hooking it between 5 and 9. We're not doing anything with that guy right there, right? You understand? And it's not even part of our circuit. So I wouldn't put a number up there if it's not what? Part of the circuit. But yeah, I've numbered this up here, right? That's numbered up there, right? All except for the start button and the stop button. But this is just showing you basically how much easier it is even to wire the circuit from a ladder diagram instead of a wiring diagram. So normally we'll use the wiring diagram for the power circuit because it's pretty straightforward, and we'll see that when we get into motors. Right now we don't have a power circuit, right? All our circuit so far is just control circuit. And then later on we'll start running a motor, and then we'll have 2 sections. Our motor is it runs off 208, and then our control logic is 120 volts, right? You understand that? And we'll get that. Any more questions?
Yeah, sure. According to that, is that 14 that's going back into X2?
Yeah, that's L2. They're doing the transformer. Now, generically, and what you got to understand, we're calling them what? I'm not even calling them L1 and L2. I'm calling them CL1 and CL2. Now, why am I doing that? Because when I look over, and this happens every time I teach this class. Over there on my 3-phase, I have a 3-phase L1, I have a 3-phase L2, and I have a 3-phase L3. This is not 3-phase over there on our control circuit, but we call them L1 and L2. I think if we look at the US Steel prints, they call them PL1 and PL2. Okay, So I'm not gonna call them L1 and L2, because why? Because somebody's gonna mess around and screw it up and say, well, there's L1 over here. And this has happened to this class. Well, they'll have L1 running over to 3-phase, and then they'll have L2 running over, then they'll have L2 running over to 3-phase. And what would happen if you turn power on our 120 volt relays hooked up to 208 volts? What would happen? What would happen to all the lights? How does power vary with voltage? If you double the voltage to a circuit, what happens to the power in the circuit? By how much? Huh? Well, guys, so I'm not changing the R in the circuit, right? You understand? So power is equal to what? V times I. But I is equal to what? V over R. So we're not changing the R on the circuit. So if I double my voltage, I double it here and I double it there. So that means if you double the voltage to a circuit, the current doubles because they are directly proportional. So what happens if my voltage doubles and my current doubles, if you double the voltage to the circuit, everything in that circuit is going to try to produce 4 times the power that it's supposed to produce. So you got a 100-watt light bulb, now it's going to try to do 400 watts. What's going to happen to a 100-watt light bulb? It's going to burn up. What would happen to your motors? They'd burn up. What would happen to your relays? They'd burn up because they're not designed to do 4 times the power. They can vary it a little bit, right? This is why, we mess around with voltage a little bit, but not much. Because power varies with the square of the voltage. How much power would it be if I took that 100, and this has happened in this class, by the way, if that light bulb over there that's designed to run on 120, what would happen if I put it on half that voltage? It's going to be very dim because it's producing a quarter of the power. So if it was a 100-watt bulb, which it's not, it would be doing 25 watts. These guys right here are maybe, 10 watts. So now they're going to be doing almost nothing, and they don't hardly come on at all. And what happened when they did that? What was wrong? They had the transformer wires divided by 4 instead of divided by 2. So instead of getting 114 volts to those bulbs, they was getting 57 volts to those bulbs, and you couldn't hardly even see the light come on. Because power varies with the square. If it goes up, it's the square. If it goes down, it's 1 over the square. So yeah, you plug this thing over the L1 and L2 over here on 3-phase, and you press that little old button there, your relay would be blown up just like that, and the light bulb would blow just like that. So that's why I'm not calling our control circuit L1 and L2. I'm calling it CL1 and CL2. So none of our circuits are going to hook up. None of our control circuits are going to hook up to L1 3-phase L1 and 3-phase L2. They're going to hook up to our L1 and L2, which is on the other side of our divided by 2 transformer, right? You understand? Now, when you hook up the motor, it's going to go up to L1, L2, L3, 3-phase. So they're calling it X1 and X2 because that's the way in fact, our transformer's not even labeled that. We don't have an X1, we have a what? We have an XF because it's what? Because that's the standard nomenclature for wiring industrial transformers. So H means the high side and X means the low side. And they didn't use L because L was already used by inductors, which didn't use I, so inductors used L. Why didn't they use I? Because current already uses I. So they screw around with, people who, the nomenclatures that were set up first, they get first shot, and then something else comes along, they get shots on down the line. So X1 and X2 on the transformer, the X side would be the what side? The low side, and the H side would be the what we call the high side. Y'all understand that? Why it's got those names? What do you mean by high side? That's where the high voltage is, right? And the L side and the X side is where the low voltage is. So if I brought my input into the X's and took my output off the H's, then we would have we'd have a step-up transformer. We could either step it up by 4 or step it up by 2. So that's why most industrial transformers don't call them primary and secondary, because they can be wired either to do what? Step up or step down. But this is only 750 kV, 750 milli-kVA transformer, or 750 watts. Transformers, by the way, are rated in volt amperes. What's a volt ampere? We talked a little bit about that in this class. So we have two ways we can rate power. We can rate it in watts, or we can rate it in something called volt amperes. So what's the difference between a watt and a volt ampere? So that's the way we calculate power, is volt times amps. So what is the difference? Anybody know? So the problem with AC, we have two types of power in most AC circuits. We have what we call true power, which is in watts. And then we have what we call apparent power, which is in volt amperes, or VA. So what we have in an AC circuit, if we got any inductors, which we do, we got a transformer, we got motors, it's going to cause a phase shift between the current and the voltage in there, which creates a power that is not the work you're getting. So you're consuming more power than the work you're getting. Transformers have to be rated, have to be able to produce apparent power, because the sources are going to have to produce apparent power. So that's why transformers are rated in VA. They're either rated, the small ones are rated in volts and amps. You'll never see them, rated in watts. But they'll have the number of volts and the number of amps. Your big transformers are going to be rated probably in kVA, because they have to provide apparent power, right? How do we calculate apparent? We have what we call a power factor. Y'all remember that? What's the power factor? I think that's on the review for the test. It's true power divided by apparent power. Now what we're shooting for is an answer of 1. If we get an answer of 1, it means they're in phase. And the work we're paying for is the work we're getting. If it's less than 1, that means the work you're paying for is not the work you're getting. And of course, most power factors get in. So if I took this and multiplied it by 100, it would be in a percentage. Alabama Power charges a penalty if you're not running a power factor of 0.95. If you run a power factor of less than 0.95, you pay a penalty in Alabama Power. I don't know about TVA. You think they would be happy about that because you're paying for something you're not getting. But what you got to understand is the power grid has got to be able to provide apparent power. So you got all this wasted power out there. That means Alabama Power is going to have to use bigger transformers. They're going to have to be using bigger conductors to handle that apparent power. So that's what they do. They charge you a penalty, not us, not residential. Our power factor is corrected for us. But industries like US Steel, they monitor that power factor all the time. And they had methods. They had some big synchronous motors out there that they could overexcite and move the power factor around to where they wanted to. So US Steel actually had a dynamic power factor correction. Alabama Power tries to do that if there's big substations. They'll have big capacitor banks that they'll dynamically switch around to try to get close to 100% as they can. And this does not occur in DC. This occurs in what? AC. True power, that's the work we're getting. Apparent power is what we're paying for. Your transformer has to deliver what? Apparent power. So that's why transformers are rated in VA or kVA. So our little transformer is rated in K. Most transformers are rated in kVA, but it's 0.725, I think, which would be 750 watts. I'm sorry, 750 VA. That's what our transformer is. So any questions? So this is BC2. This is a troubleshooting lab. We're going to deliberately, what's wrong with this diagram? We're breaking one of our cardinal rules of ladder line. Multiple loads in a single line. But they are and then they're not. So what we're going to do is we're going to deliberately start off with these push buttons up here, not press. So what's going to happen, we're coming up here with our current, and so I'm going to press the button. It comes over here, and we got two options the way we can go. We can go toward a couple of thousand ohms, or we can go toward 0 ohms. Which way is the current going to go? 0 opposition or some opposition? 0, yeah. So that means it's going to come over here, and it's going to bypass these two buttons right there, and it's going to come over here and go through our control relay. It's asking for a motor starter, but we're just going to use the control relay. So we get full voltage across our control relay. Then what we're going to do, we're going to use a meter, and we're going to troubleshoot this thing. If we're going to come over here and press one of these buttons, then what's going to happen? Well, this guy's going to drop voltage, which is going to, let's say we hit button 2. Well, if I press button 2, then it'll come up and do what? So let's press it. So I'm gonna press button 2. So it's gonna open up, right? You understand? So what's the current gonna do now? Well, the current's gonna come up through here. I press this button. It's gonna go up. It's gonna bypass, and it's gonna drop down. It's gonna go through that light and move over to our control relay. So what's going to happen to the voltage that's available to the control relay? Is it going to go up or is it going to go down? Simple question. Is it going to go up or going to go down? Is the voltage across the relay going to go up or going to go down? So if I was to draw this in DC, if I was to come over here and put this, and put this, okay, so I start off with this. These are elementary questions, guys. This in electrical, this would be like, what's your name? So if you went to apply for a job and you didn't know your name, what would happen? That wouldn't hurt. So this is pretty critical stuff, guys. Understanding what goes on in a circuit. So we started off by bypassing both our loads, and I had this circuit right here. Okay, and let's do DC. Well, if this was 12 volts, what would we have across our load? There's nothing in between there, right? We'd have 12 volts. Now what I've done is I've come over here, and I've done what? I've stuck another resistor in here. So now I know that first load can't get all the voltage, because that would mean this first one is not dropping any voltage at all. So what's going to happen is the voltage across my control relay is going to go down. What's the relay going to do with that? Yeah, is it going to stay in or is it going to drop out? Well, what we're going to find out, relays have two different voltages that they specify. They specify what we call the pull-in voltage. So that's how much voltage you got to put across the coil for it to generate a magnetic field strong enough for that plunger to come up. And the pull-in voltage is going to be quite high. It's going to be high because you got that big old gap you got to fill in, right? You understand? On your solenoid. Everybody understand that? Let's get one we can see. So here's the solenoid down here at the bottom. This is the coil. Of course, it's encapsulated. Why is it encapsulated? So usually industrial relays, they encapsulate the coil inside plastic or something. Why is that?
Don't get immature.
Dust wouldn't hurt it. This is magnetic wire, guys. That insulation out here is so thin that when I strip this, I just stripped it off. I've seen people strip it with a cigarette lighter. It just burns right off. So magnetic wire has to be extreme. The insulation on magnetic wire is extremely thin because it's got to couple the magnetic field between the different windings. If I was to come over and just nick that with something, I've tore off the insulation. I could have just shorted out 2 coils, right? You understand? So they encapsulate these so I can handle them. So if I drop them, I'm not going to knock off some chunks of insulation off my wall, off my coil. These guys, dirt don't hardly, this is where dirt hurts you up here at the contacts, not at the coil. So what I've got to do is I've got to put enough current through this thing. Of course, this thing's got a certain amount of opposition, right? I put voltage across it. It generates a magnetic field. The magnetic field generates the current generates a magnetic field, which is going to pull this plunger in. But I've got to pull it in all the way across this space right here, right? You understand? So it takes more current to pull it in than it does to hold it. So relays are rated in 2 things. They call it the pulling current. That's how much current, how much voltage I'm going to have to put across the coil itself to create enough current to create a strong enough magnetic field to move this armature all the way up against the end stops, right? You understand? Now it's already up here. So that means I can start dropping that voltage down, and so the holding current or the dropout current voltage is less than the pulling current. Because once it's up here, it wants to do what? It wants to stay up here. And that's what we're trying to do. So when I put a light bulb in series with this guy's power is going to drop by the square, right? You understand? Depending on how much it drops by. So if it's got 120 volts and that light causes it to drop to 90 volts, then your current's going to drop down by that proportional, and the power is going to drop down proportionally. And if the current drops down, of course, because the voltage goes down, then we might not have enough voltage to create enough current to keep this thing pulled in, right? You understand? So it might drop out. It's not, but it's not going to drop out because it still has enough voltage. We're still above the holding voltage. Are you okay? So when I come up here and press that other button, now what I've done, when I come over here and press this other button, moves down to here, right? Now what has to happen? Now it means the current flowing into that is going to have to go through what? 2 lights. So here we come. We're going to come through here. It's going to have to go through this one. This is going to drop a voltage. We got current flow through it. It's going to drop a voltage, right? You understand? Then we go through another one. Got current flow. It drops at a voltage. So now the voltage across our relay should cause it to drop out, but some of them don't. So what happened is we're right at the very voltage where this thing says it'll hold. So some of y'all won't drop out, some of y'all will. But what we're doing is we're deliberately causing problems in a circuit, right? Y'all understand? Are you going to see these lights come on? We might, if we come in here and turn off all these lights, you might see them come on. But remember, power varies with the square. And if we go down, it's 1 over the square, right? So yeah, we won't see the lights come on. But you'll see the results of it with the voltage drop. Everybody okay? That makes sense? No, you won't see those. You might, when you press 1, you might see one come on just a little bit, but when you press 2 of them, you're not going to see them. And what you're going to do each time is you're going to do what? You're going to troubleshoot. So you're going to put your black right there, And you're gonna start off by jumping right here, right, you understand? And right here, and right here, and you're gonna measure the voltage just through the circuit. If the relay does drop out, when you make these measurements, one of your partners is gonna have to hold the button down. Because if you don't, you're not proving anything. You're not measuring the voltage that caused it to drop out. You're gonna be measuring pretty close to zero, right? So if it does drop out, what does somebody need to do? Hold the on button, not the off, hold the on button. This is one of the hardest circuits that we wired during the term. And y'all know why? Trying to get these connections right here. This is where it's very, very important to use what? Your manufacturer numbers. You use the three button push button station because you have two buttons on there that you can either wire as normally open or normally closed. But the problem is people will leave this out here, get confused, right? So I don't have the numbers, but if this right here was 2, and then this right here was 12, and this right here was 6, then you're going to have to come down and put a wire here and then put a jumper over there, right? You understand that? So that's where we have the biggest problems. People have big problems wiring this thing. And it's not an easy circuit. And it has some manufacturer numbers on them, but you notice what I did right off the bat is I did what? Screwed them out, yeah. In fact, those look like they might be wire numbers. 1, 2, 3, 4. Did they have a number right here? 4, 5. Those could be wire numbers. And we're going to use the control relay instead of our what? Instead of our motor starter. Everybody okay? Make all voltage measurements with the on button pressed. So this is going to take both of y'all, right? Everybody okay? Any questions on this? How's it going to work? Anybody okay? It should be BC2. We don't have a test light. A little test light is just something it's usually a neon bulb, so it works with either DC or AC. And the light comes on when you have voltage and it goes off when you don't have voltage. So you'll see a lot of electricians using those things. They're really, really cheap. But they don't tell you how much voltage is there. They just tell you if the voltage is there or not there, right? So any questions on this circuit? Yes, no? Huh? Yeah, it's in BC2, figure 20. BC2, which means it would be in the BC section in experiment 2, right? This is BC4. And what we're going to do is this is real easy, guys. We're just going to use a limit switch. The book says cycle timer, but we're going to use our limit switch. Everybody should have a limit switch that y'all inventory, right? And of course, this is in my correction book. So the first thing I'm supposed to be doing before you wire the circuit is do what? Yeah. Before you wire it up, the power should have already been disconnected from your last circuit. Before you wire your circuit up, one of the first things you're going to do is check this manual up here for correction, right? So what we're going to do here is we're going to use a regular limit switch. Everybody okay on that? We're going to use the normally open thing. It's got the wiring diagram on the side. And we're just going to come up here and measure across the switch. And we're going to close the switch. How much voltage should a closed switch measure across the closed switch? How much voltage should it be? Very important concept is that. So what should the voltage, if with voltage applied, now if voltage is not applied, it's going to measure 0 for sure. If we do have applied voltage, what should be the voltage across a closed switch in the series? What voltage should we measure? Huh? So how much resistance does a closed switch have? How much resistance should a closed switch have? Almost none. In fact, a closed switch would have none. Our meters could measure. So if voltage drop is equal to I times R, let's say it's 100 amps. So 100 amps equal times 0 ohms. How much voltage should a closed switch drop? 0. A closed switch should drop 0 volts. And that's one way. If it's dropping the entire voltage, it means that switch is open, right? You understand? And that's one of the main ways we check in a series circuit. So if I got a series circuit, a complete series circuit, every one of them should drop a voltage proportional to the loads in there, right? If I find one of the loads that's dropping all the voltage, that means it's open. So the only way I'll measure source voltage is if I go across L1 and L2. Or if that switch is dropped, I can go between L1 and the light bulb, and whatever you measure between L1, it's going to be across the light bulb because the switch is going to drop no voltage. Right? Everybody understand that? Very simple circuit. Except for the next circuit. You're going to have to get this from me. You need to give it back to me in the lab though. What's diagram 30? It looks like the same diagram. But what do you notice about the symbol? I don't have lab 30, but it's almost the same. What do y'all notice about the symbol on figure 30? Yeah, if it's a diamond around it, it means it's solid state. Originally, this was marked out, guys, because we didn't have any solid state limit switches. But since we got our sensor labs, then we got solid state limit switches. And there's no manufacturer numbers on this, but it's pretty hard. There's no diagram on here, but it's pretty easy to figure out because it's only got 2 wires going to it. So this is a solid state limit switch, and this is actually a metal detector. So you're going to have some type of metal on this guy. This is an inductive sensor. Inductive sensors are nothing but metal detectors. So to trigger this thing, so it's going to be normally open until you bring some metal up here. So you could probably use one of the wing nuts up there. You got metal keys, you could probably use those, but you're going to have a piece of metal to trip this thing. Now the problem is this is an electronic circuit. It requires power to make it work. What that means is this guy has got to drop a voltage. It's got to drop a voltage, right? Because if it didn't drop a voltage, there would be no power. Because power is equal to I square R, right? You understand? So this guy requires very, very, very little current to operate. But it's going to drop about, this is not the right one. It's going to drop, I think, and you're going to measure it. We're going to have a solid state limit switch, but it's actually a metal detector. Everybody okay? Now, when you measure this, when you measure across this thing, and I don't really want y'all to measure across. What I want you to do is, so I come over here and I use the way it shows, right? I don't want y'all to measure across. What I want y'all to do is do the way you would do if you're really going to troubleshoot. Normally what we do is we take our black wire and clamp it on to the L2, right? And then I would come over here and I would take my red one and I would move it right there. Oops, that's supposed to be red, Rich. For some reason, it didn't change colors. So I'm going to take my red one and put it right there. I'm going to energize the switch, and it's going to measure whatever your line voltage is supposed to be. So let's say your meter measures 114 volts. Are we okay? Then I'm going to take the red lead and I'm going to move it over here. Oops. Sorry. I'm going to take my red lead and move it right there. What should it measure? I measured 114 volts over here. What should it measure over here? It would measure 114 because that limit switch drops no voltage. Right? You understand that? Because it's a switch. This is not a switch. This is an electronic circuit. It takes power to operate this thing. So this guy is going to drop a voltage. I think it's around 4 volts, maybe 6 volts, but it's still well within the limits of the bulb. So what's going to happen when I switch over to my solid state relay? Is over here you might measure 114 volts, and over here you might measure 110. Y'all understand why?
Checking for the voltage device.
What's that?
You measure 110 because of the
Because it's an electronic circuit that you're powering through here, and it's sharing the voltage between this. So technically this is a series circuit, but it's not, because we assume that this guy right here has zero resistance, but it don't. It can't have zero resistance and generate power, right? You understand? So this guy will drop a voltage, but it's gonna be low enough so the light bulb still works. It's gonna work fine. Because we're only gonna drop it by maybe 4 volts, right? You understand? So this is gonna be the big difference. You should notice this between the solid state relay. You're gonna measure something different between the coil and L2, L1 on limit switch. On the limit switch, whatever you measure on the coil will be what you measure over on L1, because a limit switch drops no voltage. It's not supposed to drop any voltage. But all your solid state devices are going to do that. We do have some solid state devices that we technically have to power up, but these inductive and these capacitive solid state limit switches, they don't require much power to operate. So we can power it up through the load. If I've got like an optical, one of these optical switches, what you'll find out is they'll have another wire running from here over to there, because we can't power that guy up through the load because it takes a pretty good deal of our energy to operate. But these solid state limit switches, these inductive limit switches, and these capacitors, they take almost no power to operate. So that means we can power these guys up through the load. Does that make sense? And they still drop a voltage, but they don't drop it enough to hinder the operation of the load. It's well within the limits on this. It's just like when you go out and buy an incandescent light bulb. Why they rate more incandescent light bulbs at? Most incandescent light bulbs. What's the voltage they rate those at? 110 volts. NEC says nominal voltage is 120. How much voltage do you have at your house? Did y'all measure that? Y'all was supposed to do that in your lab. Did anybody in here have 120 volts? Exactly. But all your devices operate okay because we vary the voltage just a little bit. We're okay. It's when you start varying these voltages a lot that gets us into trouble. So these are pretty good. You just swap over to this guy, and this guy don't have the manufacturer's numbers on it, but it's pretty obvious. You've only got 2 wires, guys, and it's AC. So since it's AC, it don't make any difference which one you hit the brown and which one you hook the blue to. Normally blue would go toward L1, and this would go toward L2, not to L2, toward L2. But it's AC. It would be these colors would be real critical if it was a DC circuit, but AC technically has no polarity, right? Because why? Yeah, it's changing so fast. Like I said, ours changes in a heartbeat from maximum to maximum. only 8.333 milliseconds. That's BT. Let's go to the next one, and then this is BT5. This is BT Lab 5. Here we're going to add a control relay to our solid state relay. Like I said, it's marked out. It's probably marked out in this book because it took us a long time to get some solid state limit switches in. But we have them now. So. But I want you to I'll get them for you, and then I'll put them back up because they actually belong to these sensor trains. They don't belong to you. So here they're saying, I think the title is using a control relay. First of all, most of, probably 90% of your solid state relays only have one contact. So this guy's only got one contact. It's a normally, it simulates a normally open contact. At the most, I've seen some that has a single pole double throw, which means it sounds like they have two contacts, but one of them's normally open and one of them's normally closed. So what we're going to do is we're trying to run two different lights off of a solid state relay. The solid state relay's only got one contact. And we're going to sacrifice that one contact to bring in a control relay. Now what's interesting here, guys, you need to notice this. This is a what? Normally open. What's the other one? Normally closed. So what that means is I can do this with one pole. So there's 9 to 1 gives me a what? Normally closed. Yeah. And then 9 to 3, if I get this to focus in. Still not doing it. 9 to 3 gives me a what? I'm sorry, 9 to 5 gives me a what? Normally open. But they have this common. Well, when I come over here and look at this, what is it? Oops. This thing won't switch. So we notice here we have a common, right? You'll see that? And then I could come over here and just use one pole. Well, let's come up here and erase this. So this could be 9. This also would be what? 9, right? You understand? Yes or no? And then this right here would be normally open. This would be 5, and this right here would be 1. Because the switch is wired like this. So if the switch is wired like that, then basically I can do this like that because both of those are 9.
So you just plug in the 9 and then jump from 9 to 5?
You don't jump from 9 to 5. 5's on the other side of a contact. There's something in between. You don't have to do the jumping, right? Okay. So all what I'm showing you is this guy right here. Okay. So here's 9. What does 9 go to? It goes to a normally open and it goes to a normally closed. So instead of me using two switches, and we have people do this, they'll use 9 to 1 for their normally open, and they'll use like 10 to 2 for their normally closed. Now it works fine, right? You understand? But what you've done is you've sacrificed 2 poles to get what I could have done with what? With 1. Because when I look at my diagram over there on L1, these two contacts are connected together anyway. So instead of me coming in here using 2 of my poles for something I could do with what? And we can't sometimes. They've got to have a common, right? You understand? They got to have a common connection. So the way our I don't know why it's boarding on me. So when I look at the diagram, it comes over here like this, drops down, comes over here and drops right down, comes over here and does this, right? You understand? And it labels this 9. But what I'm doing is I'm doing this now, right? Y'all understand? And then that gives me a normally open and normally, do I have a normally open connected to L1? Yes. Do I have a normally closed connected to L1? Yes. But what we're doing is we're going to do this, we can do this with one pole of our control relay instead of 2. So what we're doing, but I could literally, out of this one control relay, I could control three circuits out of this control relay right here. We've got a relay over here. We got a control relay over here. I don't know how many contacts that thing has on it. So I could take one solid state sensor that only gives me one contact, and then I could run it into a control relay that's got multiple contacts. So these are not double throw, these are all single poles. But we do have some normally closed single poles and normally open single poles. So this relay right here, this control relay right here, has 1, 2, 3, 4, 5. This one got tore off. 6, 7, 8 poles on it. So I could use my one solid state sensor to bring this guy in, and I could control 8 circuits with one solid state. So just about all your solid state sensors are probably going to have what? 1. They might have. We do have some that has that are double throws, but they're all single poles. I haven't seen one that has multiple poles in there, multiple circuits that you control. So control relays, this is a small one. This is a pretty good size one, right? You understand? And it's all controlled by one coil. A coil is encapsulated. Why is it encapsulated? But it says this guy here could run anywhere from 110 to 120 volts because it can still generate enough magnetic field to do that, right? You understand? Of course, they're encapsulated. They're usually you can't repair the coil, but what you can do is you can replace the coil. Like I said on this one, we would break this screw right here loose. Then we would take the spring off and this whole armature would pull out and then the coil would slide out from the side. And then I could come in and replace the coil and just put it back together. So this guy here is very, very repairable. The contacts are easy to replace. They're just spring loaded in there if you had a bad contact. So these are very, very popular in industry because instead of buying the whole relay, you can just buy parts to keep them fixed. So this is how when you get a flat tire, you don't go out and buy, not unless you want to, you don't normally go out and buy a new car because most of that stuff is repairable, right? Some of it's not. So another thing I wanted to make sure y'all understood is this guy right here. This is what we call a lamination. And why did I tell you that? Why we have that? So DC relays, the armature or plunger is going to be solid steel or solid metal. Usually iron, because iron is cheaper than steel, right? And iron works really, really well. So why do we have to laminate AC devices? Can you see the individual plates? Showing up real good on my screen. You'll see them? A little bit of humps. Why do we have to do that? And also they have what we refer to as a shading coil on AC right here. What this does is it prevents the relay from vibrating because AC goes to 0 120 times a second. When there's 0, there's no current flow through the coil. If there's no current flow through the coil, this thing would have a tendency to drop out like this. But before it got it anyway at all, it would put it back in. So if we didn't do something, these AC relays will literally chattel. They'll go bzzz, real loud. So what they do is they put what we call a shading coil in here. So this is basically a little inductor. And what is inductors called? Y'all remember I took it and rolled that wire around?
wire through the netting.
Yeah, and it caused a phase shift. It's been a while, but I did that when I was during church one day. Everybody stopped and looked at me. I forgot what the preacher said. He said something. But anyway, so that's happened to me before. This little shading coil on an AC relay creates enough of a phase shift to keep the relay in, which is really, really neat. You'll see the little shading coil right there? I'll pass this around. What happens, what do we need to induce a voltage magnetically? I guarantee, I ought to go and put this on the test right now. Huh?
I know if I was devastated.
We need a what? We need a magnetic field. And we need a what? Conductor. Now that's how much. We're getting the basics here. And we need a what? We need motion. So just about all metals are conductors. And this is an AC coil. So what would happen, guys, is I want this armature to react to a magnetic field. I don't want it to be a conductor. I don't want this to be a conductor. I want it to be a piece of metal that does not induce a current into it. If I had a big solid chunk of metal and I put AC on this, that would induce a high voltage into that chunk of metal, create a lot of current. We call it eddy current. That's not good. Right? You understand? So what we do is we break the conductor up. So what they do is they break the conductor up. They break it into little tiny segments so the current induced in this one does not add to that one, does not add to that one, and does not add to that one. So the little tiny eddy currents that's being induced to this guy does not add to the eddy currents being produced in that. So what happens, it allows us to use metals in an AC circuit and not let them be what? Conductors. We break the conductor up. So they call them laminated plates because they have a lamination or really, really thin insulation between each plate. So all your AC relays, anything that has to operate AC and we're trying to concentrate a magnetic field, will have laminated plates. So if I look at an AC motor, look at the rotor of an AC motor, what are you going to see? If you look at the core of a transformer, what are you going to see? You can almost see it on ours. You can see those laminations, right? Those individual plates. And what's it in there for? It's in there to so we can concentrate a magnetic field with AC without creating a big conductor, right? So the big difference between an AC relay and a DC relay is DC, we don't have to worry about the eddy currents because what doesn't DC have that AC has? What doesn't DC have that AC has? What doesn't DC have that AC has? AC has motion. So what's happening to the magnetic field? It's constantly doing what? What's the magnetic field in DC doing? Yeah, it stays the same, right? You understand. But what's happening to DC, AC automatically has motion. And this is what makes transformers work. This is what makes transformers work is AC has what? So if you put DC on a transformer, what would it do? So if I got a divide by 4 transformer and I put 120 volts DC on the primary, what would I get out of the secondary? 0. Why? Because there's no motion. So I can't induce a voltage into the secondary. DC does not induce a voltage. In fact, it would burn it up. Because what we've lost is we've lost the inductance of the thing. But yeah, we don't. Transformers do not pass DC. They do what? They pass AC. Why? Why don't a transformer pass DC? Because you don't have motion. And that's one of the three prime requirements to induce a voltage magnetically. The magnetic field has got to do what? It's got to move. We can either move it mechanically, that's the way generators work, or we can move it magnetically with AC. So if we didn't have AC, we would never have transformers. Because DC doesn't have motion. Transformers will not pass DC. You see it used every once in a while, coupling in a big heavy amplifier. They'll use what they call transformer coupling. It lets the AC signal get through, but it blocks the DC from the amplifier. So I think this is the last one we'll do before we get into motors. So we should be able to go this far already. We're fixing to go to the lab, guys. So y'all got any questions on this? So we can use a control relay for several different things. One thing we can do is we can increase the number of contacts available to a device, right? So we can let the device bring in a control relay, and then then we can use the contacts on the control relay. Everybody okay? Any questions on these? So I just gave y'all some questions.